In this lecture, we will talk about constraints again. Then we will describe how to write constraint equations related to the type of wheels. We also talk about how to obtain the kinematic model based on the constraint matrix and describe some examples. The configuration of a robot can be uniquely represented by an n-dimensional vector, which is called generalized coordinates. The vector of generalized velocities will also be n-dimensional and is indicated by q dot. The robot may be subject to kinematic constraints that include generalized coordinates and their velocities, their derivations. Constraints is represented by ai of q and q dot equals 0, in which I varies from 1 to k. You can see an example on the right side of the slide. For the standard wheel, the generalized coordinate is shown as q, and the generalized velocity is displayed as q dot. The dimension of these vectors are 3. As we have seen before, if one considers no side slipping constraint, then Vn equals 0, or y dot times cosine of theta minus x dot times sine of theta equals 0. We can write this constraint as a1 of q and q dot equals y dot cosine of theta minus x dot sine of theta equals 0. A1 is a function of theta as well as x dot and y dot. In most cases, the constraints are Pfaffian, that is, they are linear with respect to the velocities. So we can write it as I of q times q dot equals 0, in which I varies from 1 to k. For the standard wheel, we have seen in the previous slide, we can write the constraint as a1 q and q dot equals y dot times cosine of theta minus x dot times sine of theta equals this matrix times the generalized velocities equals 0. For a robot with cow wheels in matrix form, we can write all the constraints like this relation: a of q times q dot equals 0, in which a is an uppercase letter and it is a k by n matrix. K is the number of constraints, and in this equation 0 is understood as the 0 vector. Here the question arises as to what the possible movements or feasible movements could be despite these constraints. There are two cases for these constraints. One, if the constraints are partially or completely integrable into a function like hi, then we call the constraints are holonomic. For example, to analyze the movement of a rigid body like this square on the plane, three coordinates r, phi, and theta are necessary. If we pin the body to the ground with a rigid rod and fix it a rotation around the axis passing through its center, then two constraints will be created, and we can write these constraints as a1 equals r dot equals 0 and a2 equals phi dot equals 0. Both the constraints are integrable, and we can obtain h1 and h2 as you can see here. These constraints are holonomic, and the dimension of generalized coordinate will be 3 minus 2 equals 1. We have 3 generalized coordinates and 2 constraints, so the dimension of generalized coordinates or configuration space will be 1. If the constraints are not integrable, then they will be non-holonomic. In this case, the dimension of the configuration space or vector of generalized coordinate will not change. But considering that there is a constraint on the generalized velocities, the dimension will be reduced to n minus k. By considering Pfaffian constraints A of q dot equals 0, one can see that the generalized velocity q dot is a vector belonging to a set characterized by the property that every vector in this set, when pre-multiplied by aq, results in the zero vector. By definition, such a set is the so-called null space or kernel of the matrix AQ. Let's sum up the results so far. If the constraint matrix is non-holonomic, it cannot be integrated, and therefore in each configuration the instantaneous motion or velocity of the system is reduced to an n minus k dimensional space, which is actually the null space of the constraint matrix A of Q. Also, the velocity is constrained. Any configuration can be still achieved. In the general case, all feasible motions of the system can be obtained from the kernel or the null space of the matrix A. In the constraint A of Q times Q dot equals 0. Suppose V denotes the system input, that are velocities or actions. In the kinematics, we are seeking G that relates the actions and the rate of pose changes. If we look at A as a mapping from the vector space of the Q dot set to the W set, the kernel of matrix A or its null space will be a subset of Q dot sets that is mapped to 0. So those Q dots that are in the kernel of matrix A are the only Q dots that can be feasible. As a result, when G is multiplied by V, by the actions, it must produce those feasible Q dots to satisfy the constraints. So using the kernel of matrix A, it would be possible to determine G. The image of the columns of matrix G coincides with the kernel of matrix A. We will come back to this later. Let's explain this further in this example. Consider a unicycle. We seek to find G that specifies the relationship between the action V and the Q dot. There are two actions for this robot, the translational speed, Vt, which is the speed of the wheel center point, and also the rotational speed, or steering action. We denote it with omega. In this case, the steering angle is the same as the heading angle. X, Y, and theta constitute the generalized coordinates of this system. The condition for no side slipping is given with this equation. as we seen before, y dot times cosine of theta minus x dot times sine of theta equals 0. In the form of Pfaffian, we can write this equation as can be seen here. So in this case, the constraint matrix A is a 1 by 3 matrix. The feasible velocities are defined by the subspace obtained from the null space of A. If you obtain the null space matrix, the null space of matrix A, we will see that it is the span of two vector fields denoted by G1 and G2. Notice that the dimension of null space of the matrix A is 3 minus 1 equals 2. 3 is the number of generalized coordinates and 1 is the number of constraints. For number of generalized therefore it is possible to find two linearly independent vector fields G1 and G2 which are a basis for the null space of the matrix AQ, such that A times G1 is equals 0 and A times G2 is 0. By placing these vectors as columns of a matrix, the G matrix is obtained. Rate of pose change in the global reference frame, considering U as a wheel's linear velocity driving input and omega as angular velocity or steering input or steering action, the equation relating the actions and rate of pose change can be given as you can see in this slide. The number of inputs in this case are 2, and it is less than the number of generalized velocities. So you saw that in this case we can obtain the null space of A, and then we constitute G based on this null space, and finally we will have the kinematics model that relates the actions with the rate of pose change. We can add the rolling angle of the wheel to the generalized coordinates. We can add phi, which is the rolling angle. So the pure rolling constraint should also be considered. It says that there is no slipping in the longitudinal direction. So the velocity of the contact point of the wheel with the ground is 0. We can write this constraint as x dot times cosine of theta plus y dot times sine of theta minus r phi dot equals 0. R is the radius of the wheel, and phi dot shows the rolling angular velocity of the wheel. Considering both no side slipping and pure rolling constraint, the constraint matrix will be a 2 by 4 matrix. The null space of A is obtained by using mathematics. It is the span of two four-dimensional vectors denoted by G1 and G2. And using G1 and G2, we can finally obtain G. Note that here in this case, the omega and phi dot are the actions omega and phi dot are the actions. The last row of this equation is trivial. In fact, this row was created due to the use of the pure rolling constraint. It is interesting to note about this robot that any configuration QF equals XF, YF, and theta F can be reached as following strategy. 1. Turn the wheel to point to XF, YF, then roll the wheel until it reaches the point XF, YF, and finally turn the wheel to have the orientation theta F. Consider a Diff Drive mobile robot. You can see its chassis and wheels on the slide. The front wheel is inactive. Two coordinate systems are considered. First, the robot coordinate system. This coordinate system is a local frame attached to the robot and thus moves with it. This frame is denoted as XR and YR. The origin of the robot frame is defined to be the midpoint A on the axis between the wheels. The inertial coordinate system is also defined. This frame is denoted by XI and YI. The robot position and orientation in the inertial frame can be defined as QI and we express the inertial coordinates with a superscript I. Suppose the physical parameters of the robot, like D, R, and other physical parameters are known. The angular velocity of the right and left wheel is denoted by phi R and phi L respectively. Let XR and XI be the coordinates of the given point in the robot frame and inertial frame respectively. Then the two coordinates are related by the by the rotation matrix shown in equation 2. Here rotation matrix is denoted by R, and it is an orthogonal matrix. We can drop the third row and third column of R and use this equation, this matrix to convert the coordinates on the plane. This transformation will also enable to handling of velocities between frames. Equation 4 describes the relationship between the velocities in the inertial frame and the robot frame. The velocity of wheel contact point can be calculated in the robot frame. In the figure on the left, you can see the back view of the robot. The point of contact of the left wheel with the ground is indicated by PL. Now, suppose we connect a segment line from the center of the robot to the PL, which is the permanent point of contact with the ground. The distance between these 2 points always remains constant, so we can use the relationship of velocity in a rigid body. VPL in the robot frame equals VA R plus omega cross dj minus rk. D and R are indicated in the in this figure. We have assumed the velocity of the center of the robot in the inertial coordinates to be known. By using the inverse of the rotation matrix, we can have that velocity in the robot frame. So VPLR equals R of theta inverse times VA in the inertial frame plus theta dot K cross DJ minus RK. If cross product is done, the relation becomes VPLR equals R inverse times VA I minus D times theta dot I. Then we write the velocities of the contact point and center of the robot based on their components and multiply the inverse of rotation matrix. Finally, we will have x dot PLR equals x dot AI times cosine of theta plus y dot AI times sine of theta minus d times theta dot. And you can see the relation for the y components. In a completely similar way, the components of the velocity of the contact point of the right wheel with the ground can be obtained. Equations 7 and 8 shows these components. In the previous slides, we have obtained the velocity of wheels contact points with the ground. Now let's write the constraint equations to obtain the constraint matrix A. There are non-holonomic constraints that are written based on the following assumptions. 1. No side sliding constraint. There is no lateral sliding for left and right wheels. We have previously seen that the side velocities of contact points of right and left wheels are expressed by equations 6 and 8 respectively. These equations are the same, as you can see. So finally, the no side slipping constraint can be written as equation 9. Now let's express the pure rolling constraint. The pure rolling constraint represents the fact that each wheel maintains a non-contact point, one contact point P with the ground. There is no slipping of the wheel in its longitudinal axis XR. This constraint can be written using the principle of superposition. If the contact point on the left wheel moves with the chassis and does not have a rotation, its velocity in the coordinate system of the robot will be equal to x dot PLR, which has been obtained by equation 5. Now, if we only consider the rotation of the wheel, the velocity of point PL will be equal the R times phi dot L. According to the principle of superposition, the sum of these two velocities will be equal to the total velocity, which is 0. If there is no slip, there is no side slip. There is no slip in the longitudinal direction. So using the equation 5, we can write x dot AI times cosine of theta plus y dot AI times sine of theta minus d times theta dot minus r times phi dot L equals 0. Using the equation 7, the pure rolling constraint of the right wheel is obtained. As you can see here in equation 11. The three constraint equations can be written in the matrix form as seen. In this slide, you can see the constraint matrix A, which is constituted using equation 9, 10, and 11. Note that we consider the rolling angles of wheels in generalized coordinates. So the dimension of the A is 3 by 5. For simplicity, we also drop the superscripts indicating the inertial coordinate system. So the variables of the constraint matrix are described in the inertial system. Considering the angular velocity of the wheels as input, the possible velocities are obtained from the null space of the matrix A. In MATLAB, you can easily obtain the null space of the matrix with the help of the null function. If you write these comments in MATLAB, the constraint matrix will be made. Then using null function, in MATLAB, the constraint matrix will be made. Then using the null function, you can obtain the G matrix. Here, after simplification, the G matrix is obtained. Finally, with G, the relationship between actions and the rate of pose of change will be in hand. Note that here the dimension of null space of A equals 2. We have 5 components for the generalized coordinate, and we have also 3 constraints, so the dimension of the null space will be 2. Ignoring the last 2 lines, which are trivial equations, and using the following relation, I mean VR equals R times phi dot R, and VL equals R phi dot L. Finally, the equations will be in the form of equation 15, as you can see. It is obvious that equation 15 must be integrated to obtain the pose of the robot. Using the rotation matrix, it can be seen that the velocity of the center point in the robot frame is equal to R inverse multiplied by the velocity of the center point in the inertial frame. We have already know that the x component of the velocity of the center point A in the robot frame is equal to the R multiplied by the average of x dot phi dot R plus phi dot L. The y component is equal to 0, and angular velocity is equal to R phi dot R minus phi dot L over 2L. So finally, equation 18 is obtained. Please think about whether it is possible to solve the inverse kinematics of the robot with these equations or not. In the following slides, we want to talk about how to form the constraint matrix A for a wheeled mobile robot with different types of wheels. Let's start with the simple standard wheel. We want to write the constraints that arise for the robot because of this wheel. Suppose these dashed lines represent the chassis and the wheel is placed in the position shown. The coordinate system connected to the robot is indicated by XR and YR. The inertial coordinate is also located somewhere in the plane. A is the AR is the reference point on the robot, and its velocity in the robot frame is given as well as the angular velocity of the robot. We denote the angular velocity of the robot or the chassis by theta dot. We consider another reference point on the wheel, which is the center of the wheel. Its velocity equals r times phi dot. R is the wheel radius, and also we consider some geometrical parameters like L, alpha, and beta, and these parameters are in the local robot frame. Beta is the angle of wheel plane with respect to chassis, and for a fixed standard wheel, beta is always constant. AR, the reference point of the robot, and AW, the reference point of the wheel, can constitute a segment line which its length is always constant. So the velocity of point AR is given, and also the angular velocity of this line is equal to theta dot. Using the kinematic relationships of the rigid body, the velocity of AW can be written in terms of velocity of AR and angular velocity, theta dot. We can then project this velocity on the wheel plane as well as on the wheel axis direction. For pure rolling, this velocity should be equal to r times phi dot. Therefore, with a simple vector algebra task, pure rolling constraint can be written in this form. This equation is written in the frame connected to the robot. By using the rotation matrix, the coordinates of two frames are related. So we can write the pure rolling constraint in the inertial reference frame as equation 20. If you look here, you can see that we have translated the coordinates of robot frame to the coordinates of the inertial reference frame. Also, if we obtain the component of the velocity of the reference point on the wheel along the wheel axle in this direction, this velocity must be equal to 0 for the condition of no side slipping. In this case, the condition of no side slipping will be expressed as equation 21. In this way, we obtained the constraints imposed on the robot due to the existence of a simple standard wheel in terms of generalized coordinates. For a standard steerable wheel, we have additional degree of freedom. In this case, the angle beta of the wheel with respect to the chassis is not fixed anymore, but it is time varying as a result of control actions. Instantaneously, the rate of variation of beta does not have an impact on the motion constraints. It's only by time integration that the changes in the steering angle have an impact on the robot mobility. Anyway, for a steerable standard wheel, As in the case of the fixed standard wheel, the constraints can be written in the form of equations 22 and 23. In the steered standard wheel, the steering action does not by itself cause a movement of the robot chassis. But in a caster wheel, the steering action itself moves the robot chassis because of the offset between the ground contact point and the vertical axis of the rotation. The rolling constraint is identical to the standard steering case for the caster wheel, since the offset axis does not play a role during motion. The no side sliding constraint here for a caster wheel is different. The lateral force on the wheel occurs at AR, the reference point on the robot, because this is the attachment of the wheel to the chassis. So this is different than that of we obtained for the steerable wheel. A Swedish wheel is a fixed standard wheel with rollers attached to the wheel perimeter, with axes that are anti-parallel to the main axis of the fixed wheel component. The exact angle gamma between the rollers axis and the main axis can vary, and it is capable of omnidirectional motion. You can see the equations, the constraint equations related to the Swedish wheel, which are dependent on gamma, as well as the radius and angular velocity of the rollers. For a spherical wheel or ball wheel, we have the same equations as in the fixed case, but now beta gives the direction of motion and is a free variable derived from the no side slipping constraint equation. For example, if the robot translates in the YR direction, then the second equation becomes sine of this equation, sine of alpha plus beta equals 0, making beta equals minus alpha. And with this beta in hand, we can use the pure rolling constraint. So far, we have mentioned the constraints arise due to the wheels on the robot. Next, we will consider two more examples. The most familiar wheeled vehicle is a car with two steered front wheels and two fixed heading rear wheels. To prevent a slipping of the front wheels, they are steered usually using Ackermann steering, as illustrated in the slide. To define the configuration of the car, we ignore the rolling angles of the four wheels and write Q equals x, y, theta, and phi, where x and y is the location of the midpoint between the rear wheels, theta is the car's heading direction, and phi is the steering angle of the car, defined at a virtual wheel at the midpoint between the front wheels. The actions here are the forward speed v of the car at its reference point here, and the angular speed omega of the steering angle. No side sliding constraint for the front and the rear wheels can be written as can be seen here. for the front wheel, we can write x dot f times sine of theta plus phi minus y dot f times cosine of theta plus phi equals 0. Xf and yf denote the position of this point. And for the rear wheel, we can simply write x dot times sine of theta minus y dot times cosine of theta equals 0. Using the geometrical relation between the reference point and the midpoint between the front wheel's axle, which are xf equals x plus l times cosine of theta, and yf equals y plus l times sine of theta. The first constraint will be as can be seen here, and it would be in terms of the generalized coordinate x dot, y dot, and theta dot. We can finally constitute the constraint matrix as can be seen here. By calculating the null space of the matrix A, matrix G can be obtained. This is done for the rear driving robot. You can see the result here, and this is the G, and G relates the actions with the rate of pose change for a car-like robot. Please obtain G for a front driving robot in which forward speed V of the midpoint of the front wheel is the action, and also please think what happens at phi equals pi over 2 in this case, the case of a rear driving robot. The next example is an end trailer system. In this system, the first car is similar to the car-like robot that we have seen in the previous slide. In this system, end trailer are connected to a car-like robot. The point of connection of centers is the wheel axle, you can see. And the generalized coordinates here are x, y, phi, theta 0, theta 1, and theta n. And you can see x, y is the position of the car rear axle midpoint here, and phi is the steering angle of the car with respect to car body, and theta 0 is the orientation angle of the car with respect to x-axis, and theta I is the orientation angle of ICE trailer with respect to x direction. The no side sliding constraint of a steering wheel will be as can be seen in this slide. For other wheels, the no side slipping is written as you can see here, and using the geometrical constraints that you can see with these relations, finally the constraints are written based on the generalized coordinates. That's similar to the car-like robot. And with the constraints, we can form the matrix A, and then using the mathematics, we can obtain the null space of A. We will see if we do that, we will see that the null space of A is spanned by two columns of the this matrix, these vectors constitute the G matrix. In this system, there are two actions: the velocity of the rear wheel of the car and the steering angular velocity of its front wheels. In the next chapter, we will talk about the dynamics of wheeled mobile robots.